All right, so let me talk about Friday's test. I've already posted some information about it on CCLE, but just in case anybody wanted to, just clear things up, it's going to be right here in this room, normal time from 4 to 4:50. Okay, you'll have 45 minutes for the test. I'm pretty sure there's enough seats in here for all of you to spread out, so there's at least one open seat between you and your neighbor. Okay, I know you guys are kind of clumped up here and there, but so I ask on Fridays, sit so there's at least an open seat between you and your neighbor. It will cover chapters 1 through 4. Okay, today I'm going to start introducing chapter 5. Today's stuff will not be on the test. Okay, I believe. So I would recommend studying the homework problems I've assigned. Maybe your notes. See if there's anything. It's going to be all multiple choice. I might throw in just a few, quote, slightly trickier problems, kind of comparable to the questions that you might have seen, some of the clicker questions. But for the most part, it won't. I think it'll be very fair. And right now, the hardest part for me is to judge how long to make the test. So that's about it. Okay. Are there any questions? Yes. Yes, you can use a graphing calculator. So any calculator is fine, just not a cell phone. Okay. So no cell phones or iPads. Or whatever, okay? Any other questions? Okay. Yes. It will be. I will provide you with the scantrons. Okay. So it's multiple choice scantron, but I'll provide the scantrons. Okay. How was yesterday's lab? How did that go? Good. Okay. Better? All right. So, baseball and linear regression, establishing those relationships, right? Okay. So let's get into chapter 5, which is all about probability. Okay. This is chapter 5. Okay, and so this concept of probability tells us the likelihood how likely an outcome is for an uncertain event. Okay, and so, we already have this intuitive sense, okay, and of kind of what probability means a little bit, okay? So we're all very familiar with the idea that, if I flip a coin, okay, the probability that the coin will land on heads is 0.5, okay? And I think this is kind of a notion that that's very familiar to us already, and we can say something like the probability that a coin will land heads is 0.5, okay? So, as we get into probability, we have to get into this notion of what does it mean to be random, okay? And so random is this idea that the outcomes are unpredictable. Okay, we cannot know the future outcome, whether the coin will land heads or tails. We can't know that. Okay. The outcomes are unpredictable, and a series of outcomes, a series of random events, should produce no patterns. Okay, I should say in the long run. Okay, so of course, if you flip a coin 10 times, you might get heads 4 times in a row, but that's not a pattern. That's just a coincidence of heads, the coin landing heads several times. So the outcomes are unpredictable. Okay, at the same time, we can still model the outcomes with probability. Okay, so like the coin flip, we can't predict any future given coin flip, but at the same time we can say that the coin has a probability of landing heads. That probability is 0.5. Okay, and so our notion of probability, and we have words in English, synonyms for probability. Probability. These are all kind of interchangeable with the the word chance or likelihood. Okay, and so when we say the probability that a coin will land heads is 0.5, what we're getting at, and this is the frequentist view, so when we say the probability that the coin will land heads is 0.5, this is the long run relative frequency. Okay, meaning that if I were to flip the coin millions of times, the proportion, the relative frequency that the coin lands heads will be around 0.5. Okay, so after millions of flips, the relative frequency of heads is going to be around 0.5. Okay, and so that's what we're getting at when we're talking about the probability of an event. We're getting at the long run relative frequency. Okay, let's pull out our clickers, and I saw this this meme, and I think it's worth asking you guys. Okay, so it's a Velociraptor meme. Okay.
Do you like dank memes?
What's that? Do I like dank memes? Of course, right? So. It's my other dream job. All right. Okay. If the Weather Channel says there's a 50% chance of rain, does that mean they don't know if it will rain? Okay, so I mean you can replace the word chance with probability, okay? They're essentially the same. Okay, so we're gonna, I'm gonna collect the answers for this, and then I'll show you, and I'm gonna give you a second question, which is highly related to it, okay? Because I don't want to give, if I give you the answer to this one, I think it'll ruin the answer for the next one, so. Okay, it looks like we got our answers in. All right, if the Weather Channel says there's a 50% chance of rain, does that mean they don't know if it will rain? Okay, so I'm going to hit stop here. And then we'll go to the next slide, which is very similar. So I just changed it to say, if the Weather Channel says there's a 99% chance of rain, does that mean they don't know if it will rain? You can talk with your neighbors if you want about this, see if... Okay, so we'll say 10 more seconds to get your clicks in. All right, so I'm going to hit stop here, and we'll take a look at what you guys selected here. Okay, so this was question 1. Question 1 was, wait, how do I do this? Okay. All right, so if the Weather Channel says there's a 50% chance of rain, does that mean they don't know if it will rain? The answer is correct. They do not know if it will rain, okay? 50% chance of rain, they don't know if it's going to rain or not, okay? So that is the answer to question 1. Let's take a look at question 2, okay? Question 2, same thing, I just cranked up from 50% to 99%, okay? And the answer here is also, yes, they don't know, okay? In both of these cases, we are dealing with uncertainty. We cannot predict the future. The Weather Channel does not know what's going to happen, okay? The only time is only if the probability is 1 or 0 can we say we know this is going to happen or we know that this is not going to happen. In all other situations, it is it's unknown, okay? Probability really only makes sense for things with uncertainty, meaning things where we actually don't know what's going to happen. We can kind of model what could happen, and we can say this is very likely to happen or this is very unlikely to happen, but we still don't know what's going to happen, okay? In the presidential election, and there's going to be caucuses and all of this stuff, different news organizations are saying, this candidate has this % chance of winning, this candidate has, less than a 1% chance of winning. But the truth is they still don't know what's going to happen, okay? It is still technically possible for that candidate with a less than 1% chance of winning to actually win. It would be very surprising. It would be very surprising if that happened, but it's still possible, okay? And so that's what we've got going on here. Okay. All right, so let's, before I go on, I've got to talk about the difference between empirical probability and theoretical probability, okay? Okay, So empirical probability, these are probabilities based on observed outcomes, evidence. So we can think of that observed outcomes as evidence or data. And possibly simulated outcomes. And okay. So let's say you are an alien from another planet, and you have never seen this this thing. Okay, this is it's a dice, okay, or a die, and all you know is that people will roll this and see what number comes up. Okay, so let's say you have no understanding of how this works, right? Okay, but you want to know what is the probability that the die will land on the number 5. Okay? Now we know, because we understand dice, we know that this answer is 1 in 6, right? We know that there's 6 faces to the die, each one's equally likely. We know that this answer is 1 in 6, okay? But if we've never seen this before and we have no idea how this thing works, one way, this is kind of the brute force way to approach this, is we can just take the die and start rolling, okay? So, to answer this, okay, if we do not understand math, or we don't understand the physical properties of this, I should say, not math, but if we don't understand, how it works, okay, to answer this, we can just start to roll the die. Just begin rolling the die, okay? And let's say we roll it 1,000 times. Okay? And out of the 1,000 rolls, it landed on 5. We'll say 158 times. Okay? So our empirical probability, I can say our relative frequency, observed relative frequency, is 158 divided by 1,000, so that's 0.158. Okay? And this is our empirical probability. Okay? And what basically this tells us is that the next time I roll the die, has about a 0.158 probability of landing on 5. Okay? So here we still don't understand how the die works, but we know just from observation that the probability that it lands on the number 5 is something around 0.158. Maybe a little higher, maybe a little lower. We don't really know. Okay? According to the rules of probability, it should be 1 in 6, so that would be like 166 times it should land on the number 5, or 167 times it should land on the number 5. But we don't know that, okay? And we're just saying, based on our observations, we're thinking the probability it lands on the number 5 is somewhere around 0.158. So this is an empirical probability, okay? This is often used when the thing that you're trying to understand is too complicated to be able to understand mathematically. Okay, so with a die, it's very easy. You say 6 sides, 5 is one of the 6 sides, probability is 1 in 6. Okay, but what if it's something like, what's the probability that Carolina is going to win the Super Bowl? Okay, we don't have a mathematical formula to you can't just like plug in different variables and say things like, oh, the age of Cam Newton is this, and Peyton Manning looks like this, and we plug in all of these things. Okay, we don't have that. Okay, but what we do have, all right, because of modern technology, we have ways to simulate football games. Okay, I mean, you could technically go home, throw in Madden on your Xbox or PlayStation, and have the computer play against itself, right? And you can see what happens. And I think EA does some kind of promo like this. And we could have 1,000 people all have the computer play games against itself. And if it's an accurate simulation, then the results of these simulated games can give us an idea of what the actual Super Bowl, how that might result. Okay, so empirical probabilities. Let me see, where can I fit what I want to right there. I'll just say, okay, often used. So you don't have to write it up here, okay, but you can write it at the bottom. Often used to simulate or to find probabilities of complicated systems like a sports game via simulation. Okay. So when you go on ESPN and it says, this team has a 59% chance of winning, that 59% chance is derived from many simulations. And they're basically saying, in all of these simulations that we ran, this team won 59% of the time. Okay? But of course, the other team could win. Okay? Even if in their simulations, one team won 90% of the time. Okay? It's still possible that the other team wins. Okay? And that's because the simulation might not be as accurate as they thought, and there's just randomness and unknown things. Strange, crazy things can happen on the field or in a game. Maybe something happens, and who knows what. Okay. So anyway, that's empirical probabilities. Okay. Theoretic probabilities, on the other hand, okay, are determined using mathematical rules. So theoretic probabilities are determined using mathematical rules. Okay, and so the focus of chapter 5 is really learning kind of these mathematical rules to determine theoretic probability. Okay, this is kind of the focus of chapter 5. There is a tiny section on simulation, but it's like so tiny and almost trivial that it's almost not even worth mentioning. Okay, so they kind of get at this idea of doing finding empirical probabilities via simulation, but it's kind of mentioned in passing that it might not even be worth bringing up. So I think just kind of that concept of what empirical probability and how that works is important, and we'll just spend the rest of our time on theoretic probabilities. Okay, so we can define some event. Okay, an event, okay, is when a particular outcome occurs. Okay, and you know, we often assign letters to events. Or even words or short phrases to events. Okay, so we can say H is the event where the coin lands heads. Okay, or we can say A is the event that a randomly selected person is left-handed. Okay, so these are events of kind of these random trials, and these are particular outcomes. Okay, and then we would say then the probability associated with that event is written as P of said event, okay? And sometimes I will write PR, okay? But it's basically the same thing. These are interchangeable, okay? So we can say probability of heads is equal to 0.5, or probability of A, that a randomly selected person is left-handed, is 0.14, or something like that, okay? I'm just making up these numbers. Okay, so do not write okay, this is not correct. These H is the event, A is the event. It is incorrect to say the event is equal to this number, okay? This is the event. The event does not equal a number, okay? You must say the probability associated with the event is equal to some number, okay? The event is not a number, okay? Okay, unless you're talking about the event that a randomly selected number is 0.2, but then you have to write it that way, okay? The event itself is not 0.5. The probability associated with the event is 0.5, and there's a distinction there. Okay? All right, so all probabilities are between 0 and 1 inclusive. Okay? So for any event A, and actually, maybe I'll just throw this on the next slide, just because it's going to get too crowded here. Okay, so all probabilities are between 0 and 1, and that means for any event A, the probability of A is less than or equal to 1 or greater than or equal to 0. Okay, and this is a good way to check your work. Okay, if the probability ends up being negative, less than 0, is outside of this range. Okay, that is, negative or over 1. Okay, you have made a mistake. Okay, it is not possible to have probabilities greater than 1 or less than 0. Okay? For some event A, okay, we define the complement and this is complement spelled with an E here, of A as the event where A does not happen. Okay, and so we can say, you know, the complement of A is equal to A complement, or we can also just write not A. Okay, so these events, the complement of A is the event that A does not happen. So if A is, we pick someone who is left-handed, the complement of A is we pick someone who is not left-handed. Okay? If A is the coin lands heads, then the complement of A is that the coin does not land heads. Okay, and we might say, well, if the coin doesn't land heads, then that must mean it landed tails. Okay, and we can say, well, we can define things that way, but that's how it goes. Okay, so we write the probability of A's complement. Okay, the complement of A, the probability of A complement is equal to 1 minus the probability of A. Okay, and these two outcomes cover all possible scenarios. Okay, right? So whatever event we're talking about. Okay, I'm going to pick someone at random. Okay, and we can say A is the event that this person is left-handed. Okay, if I pick someone at random, the person I select is either left-handed or that person is not left-handed. Okay, there's no other possibilities. That covers all possible situations. It's either left-handed or not left-handed. Okay, or this person, you know, has this attribute or does not have that attribute. Okay, so another way to think of it is that the probability of A plus the probability of A complement, these two add up to 1, right? Okay, and this is just algebra moving terms around. But we're basically saying that the situation where A or its complement occurs covers all possible situations, right? Covers all possible scenarios. Okay. All right, let's look at question 3 here, and let me get the clicker running here. So the probability of A and its complement is probability of A and A complement We have a question?
Is this referencing them both occurring at the same time?
Huh?
Is this referencing them both?
Correct, correct. Okay, we'll just say a couple more seconds here. All right, let's see. Let's see what you guys selected. Okay, so this is the probability of A and its complement. So this is different from what I had written where this is the situation where A or its complement occurs. It says the situation where A and its complement, okay? So we're kind of split between A and B, and then some people thought maybe it's D, okay? The answer is A, okay? It is not possible, okay, so you have to think of this, right? If, let's say we define A as being someone, a person I randomly select being left-handed, okay? What is the probability that a person I randomly select is left-handed and not left-handed? That's what we're asking, right? What is the probability, if A is someone is left-handed, what's the probability that someone is left-handed and not left-handed? Okay, that's an oxymoron. It's not possible. You cannot be both something and not something at the same time. Okay, unless we're talking about Schrodinger's cat, it doesn't work. Okay, so you cannot be one thing and not that thing at the same time, and so the probability of that is 0. Okay. All right. Okay. So this brings up an interesting kind of a topic called mutually exclusive events. Okay. Mutually exclusive events means the probability of two events. The probability of two mutually exclusive events happening together is 0, okay? So if A and B are mutually exclusive, then the probability of A and B is equal to 0. Okay? It doesn't matter what the probability of A is by itself or what the probability of B is by itself. Okay? Mutually exclusive means the probability of A and B together is equal to 0. Probability of, okay, so those are mutually exclusive events. So this could be, you know, A could be a randomly selected card is red, and B is a randomly selected card is spade. Okay, so you know, if you're familiar with a deck of cards, you know that half the cards are red, so you can say probability of A is 1/2, and if you're familiar with a deck of cards, the probability of B, that a card is a spade, 1/4 of the cards are spades. Okay. However, is it possible to draw a card that is both red and a spade at the same time? No. Okay, so if we look at a deck of cards, okay, all of the spades are black cards, okay, which means there's not a single spade that is red. So it is not possible to draw a card that is both red and a spade. So spade and red are mutually exclusive outcomes. The probability of A and B is equal to 0. Okay? So likewise, I think it makes sense to say that A and its complement are mutually exclusive, okay? Because you cannot be one thing and not that thing at the same time. Okay, we have events with simple outcomes. Okay, simple outcomes are possible outcomes to event, and all of these outcomes are equally likely. Okay, so all simple outcomes have an equal chance of happening. Okay, so some examples. Okay, rolling a die. Okay, the outcomes are 1 through 6. Okay, all are equally likely. Okay, or we could, select a person from the classroom at random. Okay, our outcomes is each person, every single person. Okay, all people in the room. Okay, and every person has an equal chance of being selected. Okay, so these are situations where we have simple outcomes, okay? And so if we've got some event A consists of, several of these simple outcomes, okay? Okay, then the probability of A is equal to the number of outcomes included in A divided by the total number of possible outcomes. Okay? So for example, let's say we're talking about rolling a die. And we will say A is the die lands on an even number. Okay? So A consists of the outcomes 2, 4, and 6. So the probability of A, how many outcomes are part of A? There are 3 possible outcomes in A. There are 6 possible outcomes total because there are 6 faces to the die. So the probability of rolling an even number is 3 out of 6, or 0.5. Okay, we have to be careful, okay? In some situations, we might think we have simple outcomes, but they are not simple outcomes, okay? So we cannot treat this as such. So let's say we roll 2 dice. Okay, all right, and then we look at the sum of the 2 dice. Okay, well, the outcomes are when you roll 2 dice, you can get 2, 3, 4, 5, 6, all the way up to 12. These are the possible outcomes, okay? And if someone says, what is the probability of rolling 2 dice that add up to 7, okay, it is wrong to say, well, we have 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 outcomes to say 1 out of 11, okay? Because each of these outcomes are not equally likely. Okay, it is, much easier to roll a 7 than it is to roll a 2. Let me just hop online for a second here. Copy this. Okay, so what we have to do is we have to model this. We have to model the 2 dice as each one of these, there are, if we look at this, there are a total of 36 possible outcomes, okay? And if we look at how many add up to 7, we have 1, 2, 3, 4, 5, 6, okay? So here we see it's not 11 outcomes, we actually see there are 36 possible outcomes. Okay? And each of these 36 are equally likely. Okay? So in this scenario, the probability of rolling a 7 is equal. We have 6 possible outcomes out of 36. The probability of rolling a 7 is 1 in 6. Okay? All right, so you always have to make sure that whatever you're talking about, if you're going to use this simple outcomes rule, that they truly are simple outcomes and that they all have equal probability of appearing. Okay, we'll end there. We'll see you guys on Friday for the test. Good luck as you guys